Welcome to the third in the FECO webinar series for 2013. For further information on FECO, please visit our website www.feco.info or contact your local distributor. You are also welcome to contact us via the email address that appears at the end of the presentation, webinars@feco.info. Dani Ludek, one of our kernel engineers at EMSS, will now present Intelligent Design with Characteristic Mode Analysis. Over to you, Dani.
Thank you very much, and welcome again to all our listeners on this presentation based on characteristic mode analysis and how one can use this to gain insight into the radiation properties of your design, such as antennas. Now, before we dive into the details, I thought it might be useful to first give you a bit of an overview as to what we will speak about today. So I think as a start, it would be useful to give you a bit of background on what is characteristic mode analysis. Then we will go over to a bit of terminology that is used for this method, not specifically only the definitions, but also why certain quantities are important or relevant and why it's used. I will then go over to discuss a topic that is of interest in this field called mode tracking and how we went about that to solving that problem with our characteristic mode analysis solver. I will then illustrate to you or explain to you how CMA is integrated into our FECO suite so that it is comfortable for you as a user to use this feature that we offer. I think, however, a good way to understand a method is not only to listen just about the theory and formulations. It is also good to illustrate how this can be used at the end of a few examples. And I will cover 3 examples in this presentation, the first of which is using characteristic mode analysis to design a multi-mode MIMO antenna. I will then go over to explain how characteristic mode analysis is applied to larger or electrically larger type of structures. And then I will speak about a topic that is frequently encountered in the field of characteristic mode analysis, and that is mobile phone design. And then I will conclude my talk. I just want to emphasize again that if you have a query or a question, you can send this to an email address that will be listed on the last slide. Now, firstly, what is characteristic mode analysis? I will refer to characteristic mode analysis hereafter in the rest of the talk as CMA. Basically, CMA is the numerical calculation of a weighted set of orthogonal current modes that are supported on a conducting surface. This is very similar to waveguide modes that are illustrated at the bottom left-hand side of this slide, in that it is essentially the building blocks of a certain solution. Illustrated with waveguide modes, it is the field, or we decompose the field, but with characteristic mode analysis, CMA, we decompose the full wave current into individual current modes. Now, on the bottom right-hand corner, the first 4 current modes of a simple structure, which is a plate in this case, is shown. And I will explain to you a little bit later what other properties of these current modes are. But I think it is important to note at this stage that it is a way to decompose your solution into its fundamental building blocks. And the reason that you do that is, in some cases, it is much easier to extract information about your structures using these individual building blocks as opposed to the full wave solution. And this theory is not new or novel. It was actually proposed in the 1970s already by a person called Garbat. And then it was later refined by the famous Harrington and Mouts in their transactions article. Now, a good question at this stage is, why do we want to calculate these current modes or individual building blocks of a reference solution? And basically, the points are, or the reasoning is, that it allows for a systematic or a non-brute force computational electromagnetic design approach. Frequently, we encounter in antenna design, people design antennas, but without really understanding all of its fundamental properties. Problems are typically passed towards optimized solvers or optimization algorithms to gain a certain dimensional configuration from which you gain an answer. And people or designers typically follow this route without really understanding why certain antennas radiate as they do, or what modifications can be brought about in order to improve its performance. Now, characteristic mode analysis brings us back to the basics, and as I said here, allows for a systematic design approach to be followed. It provides physical insight regarding the antenna operating principles, and it can be used to determine the resonating frequencies of specific modes so that we can optimize our designs to work or to function properly by enhancing this modal behavior. We can also determine, as I will show later, optimum feeding arrangements to excite certain modes. And on this last point, I went and I found a very nice example that was compiled by the reference shown at the bottom of the screen by Marta Cabedo Fabre in the reference that is explained in the reference listed there. And the idea was to excite or to find an optimal placement of a feed on a triangular patch antenna in order to excite circular polarization. Now, without going into the details, what they basically did was to find a location on this patch structure to excite two orthogonal current modes that in essence provided this circular polarization. And by using characteristic mode analysis, they could identify where to place the feed. This is a very brief overview of that example, and for further or more details, I would refer all our listeners to read that very nice reference listed there. Now, just a little bit about the formulation of the characteristic modes. Characteristic modes are obtained by solving an eigenvalue equation that is derived from the method of moment impedance matrix. And we do this by separating the MOM impedance matrix into a real and imaginary component, as illustrated here. And from that, we can then formulate an eigenvalue equation. Now, in that equation, X and R are our imaginary and real parts of the impedance matrix respectively. Lambda is our eigenvalues, and the vectors I subscript n is the eigencurrents. When we solve this eigenvalue equation in this way, we obtain real or equiphasal eigencurrents. Now, what is very interesting to note at this stage is that the eigencurrents are essentially independent of any specific source or excitation. It depends only on the shape and also the size of the geometry. So this again emphasizes what I mentioned earlier, is that it brings us back to understanding the fundamental properties of our radiating structures. Now, with all this said, I will explain to you a few definitions in the CMA or terminologies that are used in this field, and also why these terminologies or definitions are important. The first definition is what exactly is a characteristic current or a characteristic field. Now, characteristic currents or fields are the real orthogonal eigenvectors and also the associated field quantities that are the solution to the generalized impedance matrix or generalized eigenvalue equation that I showed on the previous slide. And these quantities are important in that it shows us or illustrates various possible currents or also fields that are supported naturally by the structure that we are considering. Now, the structure here shown on this slide, I show the first four eigencurrents and also characteristic far fields of a simple square PEC plate. But by looking at the eigenvalues, we can gain some more insight. Now, the eigenvalues, or the lambda subscript n, are obtained when we solve the eigenvalue equation and provides us useful information, especially when we plot this quantity as a function of frequency. And the reason that this is useful is because its magnitude is proportional to the reactive power. So this in turn tells us that modes resonate more efficiently as the magnitude of the eigenvalue tends towards 0. But that's not all. Its sign also gives us some very interesting information. When the eigenvalue is larger than 0, this mode is essentially storing electric energy, or it is a capacitive type of mode. When it is smaller than 0, this mode is essentially storing magnetic energy, or it can be seen as an inductive type of mode. And as I mentioned, as it tends towards 0, this mode starts to resonate. Now, I illustrate here on this graph the eigenvalues plotted between 1 and 5 gigahertz for this square or for this rectangular PEC plate. And we can see that around 2.4 gigahertz, this plate is of resonant type of length. Now, when looking at the first eigenvalue, we see that this corresponds to our theory in that it's 0, round about 2.4 gigahertz, where this mode resonates. I think also at this stage it's useful to mention that our eigenvalue solver returns the modes according to this quantity. For example, the order in which the modes are returned, that is mode 1, 2, 3, and 4, are in the order in which it radiates efficiently at a certain frequency. And this concept will again be explained a little bit later when I talk about mode tracking. But the problem is if we can just skip back to the previous slide, extracting resonant properties of different higher order type modes at higher frequencies might become quite difficult, because now we get graphs like this, that is where they are quite tightly grouped, we cannot really make any distinctions between them. And for this specific reason, other quantities are also defined that allows for a better visualization of the resonating characteristics of the mode. And these two quantities are called modal significance and also characteristic angle. And it's basically just a different way of extracting the eigenvalue information to obtain the resonance properties of the particular modes. Now, on this graph on the left-hand side, I show to you the modal significance of the previously mentioned rectangular PEC plate. That is also plotted here as a function of frequency from 1 to 5 gigahertz. And now, if I can show to you the modal significance equation, we see that it's 1 divided by the magnitude of 1 plus j times the eigenvalue. And if the eigenvalue tends towards 0, that is when the mode starts to resonate, this value here, the modal significance, will go towards 1. And this is exactly what we are seeing here for mode 1, is that it starts to resonate near 2.4 gigahertz. Also, another way that we can obtain information is by looking at a quantity called characteristic angle, which are defined as illustrated here. Now, again, as the mode goes towards 0, that is, as it starts to resonate, this quantity, the characteristic angle, will tend towards 180 degrees, as indicated here on the graph. Other quantities that we can also extract from using the eigenvalues are the concepts of modal excitation coefficients, modal weighting coefficients, and also modal input power. Now, up until this point, I emphasized that characteristic modes is obtained by solving an eigenvalue equation in which there is absolutely no source present. And this is true, this is still true, but sources are, however, present in practical antenna type of examples or radiating examples. Now, the question is, how do we account now for the effect, or how do we see the effect of sources on our modal decompositions? And we can do this by applying or by calculating the quantities that I list on this slide. The first of which, let's start here with the modal excitation coefficient, which can be defined as illustrated here in the numerator. This quantity essentially tells us how efficiently does a mode, illustrated here by J subscript n, couple into the incident or the source, which is basically a vector, illustrated here as E superscript I. And this quantity, as a mode couples more efficiently, or as the excitation couples more efficiently into the mode, this quantity will become larger. But, as I also illustrated with the previous graphs, the eigenvalues are important in that it tells us how efficiently or how easily a mode can be excited to radiate energy. So obviously this quantity should also be taken into account. And a parameter that is defined by taking both of these concepts into account is the modal weighting coefficient. And we use the modal weighting coefficients to scale each of our individual current components in order to synthesize our full wave current. Now, it is important also to explain or to note that for this equation to be valid, we assume that the modes are normalized such that they are orthogonal with regards to the real part of the impedance matrix. And this is also termed our orthogonality. This concept will also be explained or emphasized a bit later when I talk about mode tracking. Now, these quantities are all very interesting, but it's not useful, but another way of looking at it perhaps is when we talk about modal input power, that can be defined as the input power in each of the modes. And we can calculate this by calculating the square magnitude of each of our modal weighting coefficients, as illustrated here. Now, this may seem like a mouthful, and it's also always useful to illustrate the concepts with the hand of an example. So let's take a very simple example, which in this case is a half wavelength dipole antenna that I excite here at the center point with pin feed. It's of resonant, as I said, it's of resonant type of length. And now I simulate this, and from that simulation I extract the full wave reference solution, which is illustrated here by the green line, and also the first three modes, J1, 2, and 3. And I plot this here as a function of the segment index. That is, this line or the dipole is discretized with different segments. So this graph essentially just shows you the current distribution over the wire dipole. Now, as we can see here, because our first mode or our fundamental mode couples very efficiently into our full wave reference solution, I also showed here higher order modes that are supported on this structure. But at this, if we should excite the structure in this particular manner, we see that our excitation couples very efficiently into our first mode by looking at the relative mode power that is contained in each of our modes, which these quantities are rounded, but we see that essentially all of the power is contained in our first mode when we excite the structure like this. Obviously, as the example, or as different types of structures or different excitations are considered, these power distributions will vary between the modes. Now, as I mentioned, I would like to discuss a topic called mode tracking with you. The concept of mode tracking can be explained by looking at a graph like this, which shows the characteristic angle as a function of frequency, but for a more complex example, which is a patch antenna on a dielectric substrate. The problem is that at each frequency iteration, we solve the generalized eigenvalue equation, and we gain a set of eigenvectors and also eigenvalues. But as I mentioned earlier, these quantities are sorted according to modal significance. That is, they are sorted according to their resonant behavior or resonance behavior. Modes can therefore be incorrectly mapped at subsequent frequencies because higher order modes may become more dominant at higher frequencies than they were at, for example, lower frequencies. Now, as I show here, this mode, which is J2, essentially swaps at this point with a higher order mode that is not being accounted for on this graph. And in summary, we cannot use characteristic angle or eigenvalue equation graphs plotted as a function of frequency if we see this jumping type of behavior. So the way that we want to go about this is to transform untracked graphs, such as the ones shown here at the bottom left-hand side of the screen, into tracked graphs, from which we can deduce much better where the resonating properties of certain modes are. Now, we go about this, I just want to briefly explain to you our tracking approach. What we do is we look at the eigenvectors and not at the eigenvalues or so on. For our tracking algorithm, and the reason that we look at tracking eigenvectors is because they change more gradually with frequency. We also apply, we use the R-orthogonality property of the eigencurrents that I just want to summarize here again, in that if a mode is correlated, we can refer to this, or I will refer to this as a function, as a type of correlation. If we apply this formula to modes of the same indices, we gain a value of 1, because we also normalized our modes in order to obtain this. But if we should look at modes where the indices are not equal, that is different modes, they should not correlate in any way, and the value here should be 0. Now, our reasoning is that for lower order modes that are requested, this quantity should also be valid between adjacent frequencies. It won't be exactly 1 or 0, but it will give us a good estimate as to which modes map to which other modes, in that we can identify the mode progression between the frequencies. And by using this property, we then set up a ranking or a mapping vector so that we can correctly rank our two-dimensional graphs with respect to the starting frequency. It is also, however, important to mention that the frequency increment should be small enough for efficient correlation to work. It is also envisioned that for future work we will include this frequency refinement more automatically into our suite. A key point, however, with this tracking approach here is that we do not need to calculate or track all of the modes. That we can track only the number of modes that the user requested. Now, before I show some examples, I would like to show to you or explain to you how characteristic mode analysis is integrated into our FECO suite. And I can do this as I'm sure many listeners have been using CMA with FECO, but not directly. That is, following a more manual approach. This approach is summarized on the left-hand side here. That has been the process flow from FECO Suite 6.1 and earlier. So the key components, or the manner in which you would do a characteristic mode analysis using our toolkit, is you would use FECO to calculate or set up a certain problem, that is a method of moment solutions, and then export the method of moment impedance matrix into a match file. This file could then be read back into a toolkit such as MATLAB, and then you would write your own script in which to separate the real and also the imaginary components. And but you can also then further extend your script to implement your own eigenvalue solver, or use a solver inherently available in tools such as MATLAB, provided by functions such as I. And now you will gain a set of eigenvectors and also eigenvalues. You could then read these eigenvectors or write your own solution files or STR files that you can read back into FECO, and then you will be able to view the eigencurrent distribution or in FECO or in our post-processing toolkit. And since FECO Suite 6.1, that is from 6.2 and onwards, we have been focusing on fully integrating this characteristic mode analysis design into our whole FECO suite. And now it is only necessary for a user to specify the number of modes that he wishes to request in our GUI component. You can also specify which quantity would you like to calculate for each of the modes, that is currents and charges, near fields or far fields, and the results, the simulation is performed and the results can be viewed in our post-processing tool. So just to focus on the first step here, you can specify using our characteristic mode configuration the number of modes that you wish to calculate for any generic type of structure such as the one illustrated here. And from FECO Suite 6.3 and onwards, you can also choose to include the effect of the excitations by letting FECO also calculate the effect of modal excitation coefficients if sources are present. But if sources are not present, that is not a problem. As I said, characteristic mode analysis is essentially a source-free solution to obtain the fundamental characteristic behavior of the structure. So as you specify only the number of modes or a certain subset of modes, our kernel or our suite then solves this or calculates the eigencurrents, which we can then view again in our post-processing toolkit. Now, in our post-processing tool called PostEcho, we offer three-dimensional graphs for the currents and charges, near fields and also the far fields that are associated with each of the modes. We also offer two-dimensional graphs for plotting the eigenvalues, characteristic angle, modal significance, and so on as a function of, for example, frequency. And scripting is also available in which we allow users to add weighted modes together and view, for example, the effect of combining, say, modes 1, 2, and 3, each weighted by a certain complex coefficient. Now, let us go over to looking at a few examples. The first example is the design of a multimode MIMO antenna using characteristic mode analysis. Now, before I go any further, I would like to credit this design to this reference mentioned at the bottom of the screen here, which was illustrated in the radio engineering, also done by the Spanish research group that is that's also been active in the field of characteristic mode analysis. So for detailed insight into this example, please refer to that reference. But I will try to go over some of the key points of that article. Now, the motivation here, or a bit of background to the problem, is MIMO, or multiple input, multiple output, is used to improve throughput for wireless applications, such as example cellular networks. And they do this by using multiple antennas on a handset. The motivation for doing this is that people are constantly looking for example, cell phones that get smaller and smaller and that should function faster and faster. But using MIMO is not that easy. It is quite a difficult task because multiple antennas on a small, on a limited amount of space also exhibit a large degree of mutual coupling. And now, this might become a more complex design for an antenna engineer. Now, a possible solution that was applied in this work is that one can also use different orthogonal radiation patterns that are produced by the modes, the characteristic modes of an antenna, that is calculated using CMA. And the structure that will be considered is this ring type of a resonating structure here. Now, applying CMA to this problem entails firstly calculating the, shown here, the first four eigencurrents or also characteristic fields. Now, I only show the first four here because these are the dominating radiating components at around our design frequency, which is about 2.4 gigahertz. We can also see that because this is a symmetric structure, some of our modes will be rotationally symmetric, such as mode J1 and mode J2 over here. Other modes, such as the one illustrated here, exhibit sort of inductive type of behavior. Now, this inductive behavior is also evident when we look at plots such as the characteristic angle as a function of frequency. As I mentioned in the onset of the presentation, the characteristic angle as a function of frequency tells us where does a particular mode resonate, and that happens when the mode or this curve crosses 180 degrees. Now, as you can see on this graph over here, this black line, which is the characteristic angle associated with mode J3, the inductive type of mode, does not cross this line at all. In fact, it remains below 180 degrees. Now, as you can recall, I said that by looking at the sign of the eigenvalue, we can also deduce valuable information. So we again establish that this mode is in fact storing inductive type of, or storing magnetic energy. And our goal now is to optimize or to mitigate this effect in that to get that mode to radiate. Now, before we go into the details of how to go about that, I think a question that typically pops up when considering CMA is how do you excite these modes in any case? Now, for this type of a structure, when we do a CMA analysis, we can identify certain current maximums at locations. And this is exactly where we can place our feeds, that is at places of high current intensity. But we can then also get the correct current direction by applying the correct phasing. So on the left-hand side here, I show how we can simulate this inductive type of mode if we phased or excited the structure in this way. On a similar basis, we can also excite a higher order mode, J4, by exciting the structure in this manner, where the phases have now changed. Now, let's go back to how are we going to mitigate the effect of this inductive mode. Now, if you can recall from any engineering undergrad course, the way in which to counteract inductive behavior is to add some form of a shunt capacitance. But we can't just go about adding shunt capacitances everywhere because we might alter the behavior of other type of modes. Now, characteristic mode analysis also gives us useful information in where to start modifying structures without disrupting the behavior of other modes. And we can do this by considering current nulls or places where the current is a minimum. And for mode J4, this will be around these regions here, illustrated by the green arrows. So if we now go about introducing these slits or slots, we can add a capacitive type of behavior. And it's non-invasive in that it doesn't really alter the behavior of mode J4. So the question now is, did our design work as we expected? And we can again emphasize this or look at whether it worked or not by considering the characteristic angle of our new configuration as a function of frequency. Now, on the left-hand side of the screen here, I show the original curve, or the black line here represents the characteristic angle that is associated with mode J3, the inductive mode, and the yellow line here shows the characteristic angle that is associated with the fourth mode, the mode that we didn't want to alter. Now, by introducing the slots, we have essentially improved the radiation characteristics of this mode J3 in that we now essentially pulled it up to cross the 180-degree curve round about close to our resonating frequency of about 2.4 gigahertz. And as you can note here, the behavior of the yellow curve mode, or the characteristic angle associated with mode 4, has not been changed in any way. I hope this example shows to you just some of the considerations or some of the systematic approaches that can be followed with a CMA in order to obtain a suitable design. And again, I would like to emphasize that if you have, or if you would like to read a little bit more, please visit or extract this reference that I mentioned on the slide over here. Now, next is I would like to talk a little bit about the characteristic mode analysis of larger type of structures. Now, characteristic mode analysis is a solution technique that is based on solving an eigenvalue equation based on the method of moments. Now, the method of moment entails that we need to discretize a structure in terms of subsectional basis functions, typically used are Raworth and Glisson basis functions, that is spans a triangular type of domain. Now, for simpler structures, such as the MIMO antenna considered in the previous example, the number of unknowns may be quite limited, or it may be less, and our eigenvalue solver can get answers quite quickly. But as the number of basis functions become quite large, so does our computational complexity, or the time and memory required to obtain a characteristic mode solution becomes more and more. And what I want to illustrate with this example is what type of solution did we implement, or how does our solver go about calculating these quantities in an efficient and quick manner. Now, I just want to illustrate here without going into too much detail, the vehicle type structure that has been analyzed, or the first 4 modes has been solved at about 35 megahertz. And illustrated here, I show you the eigencurrent distribution. On a similar way, I can also show you the far field distributions of the first 4 normalized characteristic near fields, and also that of the far fields. Now, our characteristic mode solver is based on calculating only the number of modes that have been requested. And this is as opposed to calculating all the modes that are supported on the structure, which is in the order of the same number of unknowns used for the discretization, which if we think about the car, it's in the order of about 10,000. Now, if I can draw your attention to this table here, if we should apply a solver or characteristic solver, eigenvalue solver, that is based on calculating all of those modes, we can wait about 11 hours to get an answer and use about 3.5 gigabytes for the solution. Now, as I said, our CMA solver is based on solving only the subset of the modes, because not all of the modes may be important in the radiation characteristics. Now, if we should calculate the first 4 modes, the result of which I've shown earlier, we see that our time for calculating these first 4 modes reduces quite significantly from about 11 hours to 330 seconds. And so does our memory usage also reduce quite a bit. Now, we've also added parallel support in that you can use multi-core or multi-CPU environment in which to parallelize this solution in order to get the answer even more quicker. And something that is also fundamentally inherent in an eigenvalue solver is the use of GPU acceleration, which has also been added to our technique for further to obtain answers much more quickly. Now, illustrated in this table is the effect of applying, say, a Tesla GPU to calculating the first 4 modes of the vehicle type structure. And as you can see, the CPU time for the CMA solution reduces from about 330 seconds to just under 10 seconds. So we have now essentially obtained an answer that would have taken about 11 hours should we have calculated all the modes. We've reduced that time to just under 10 seconds by applying also, as a final step, the GPU architecture. We can also apply multiple GPUs to gain the benefit of multi-core type of simulations. Now, a topic that is typically analogous with, or typically used in characteristic mode analysis is that of mobile phone design. Now, mobile phone design with CMA is useful because characteristic mode analysis offers fast insight into the fundamental resonant behavior of the different components of a phone, such as the ground plane, glass cover, battery packs, speakers, housing, and so on. Here I showed you just 2 examples of typical models that are used for to represent mobile phones. That also includes the effect of the glass, different feed structures. In the case of the top hand here, we also have a dielectric present in our feed structure. Now, because we don't want to work with such a very complex design, we would like to, antenna or mobile phone engineers typically simplify the model. But the question is, to what degree can we simplify a model without now missing some of its fundamental radiating properties? And I think a good way to illustrate this is to consider two basic models of a ground plane, one that includes the effect of the source and the other without the effect of the source. Our goal is to obtain to what degree can we work only with the ground plane by omitting the feed structure without severely penalizing the effect or without missing our fundamental resonant behavior. Now, on the top-hand corner here, I showed to you the first 3 modes of this structure that is illustrated with the feed. And I also want to emphasize here that the feed contains dielectrics. So our characteristic mode analysis solver can solve problems that also include dielectrics, that is modeled using surface equivalence principle. If you would like to gain a little bit more information on this feed structure, I refer to this reference over here that was published in the Microwave Journal. Now, to get back to the point here, we solved this model with the feed, with characteristic mode analysis, and obtained the first 3 modes. I then also calculated the first 3 characteristic modes, but without the feed structure. And we see, to a large degree, our resonant mode behavior has been is also reflected. So we can work with, in this case, working with a PEC plane, a ground plane like this, to a large degree, is sufficient, or it gives us confidence in our simulations, working only with a model like that. Now, one thing that may be required in phone design is to identify places in which to modify the ground plane. This can be to accommodate, for example, wires or different components, etc. Now, as I illustrated also with the MIMO antenna example, CMA can illustrate positions where to do this without affecting the dominant mode behavior, and that we look at places where we have current nulls. Now, on this example, we can see that there is a big current null in the center of the plate. But if we should now, for example, in an extreme case, cut a slot out over there, did we alter the radiating properties? We can ensure that we did not by looking at quantities such as the characteristic angle as a function of frequency. And these 2 lines are associated. The blue line is associated with the full model, and the green one with the one with the slot. And in this case, we see that there is very little difference between the models. This just gives us confidence in this design step. Another way in which characteristic mode analysis can be useful is to excite a desired behavior or a desired modal behavior by including also the effect of sources. Now, illustrated here is a mobile phone model with a complex type of feed structure. And as an antenna designer, we would like to know where can we best excite this structure to obtain a desired behavior, and we can identify this desired behavior by looking at, for example, the individual eigencurrents. And we would like to excite this type of mode behavior over here. Now, by looking at a graph of modal weighting coefficients, which essentially includes the effect of sources and the eigenvalues, we can see that by iterating through a few excitation positions or excitation schemes, we can optimize this particular mode over here, in which that we should expect this mode behavior then to closely correlate with that of the full wave reference solution. And we can again check this by firstly calculating a full wave solution, or that is just a plane method moment analysis of our structure, and comparing this to our characteristic mode analysis that is associated with this particular mode that we would like to excite, and correlating with the graphs shown on the previous slide, we see that the behavior is very much the same. So modal weighting coefficients provide us with a way in which to optimize a certain mode behavior in order to closely resemble that of the full wave operating principle. Now, in conclusion, I would just like to summarize by saying that characteristic mode analysis provides a designer with deeper insight into the radiating properties of arbitrary geometry, such as those that are discussed in this presentation. Quantities such as the modal input power and modal weighting coefficients can also illustrate the effect of the external sources, such as I explained at the hand of the modal of the mobile phone example, and also the simpler dipole example. These curves, especially when considering two-dimensional curves of characteristic angle versus frequency or eigenvalue versus frequency, is not very useful if modes are not properly tracked as a function of frequency. We have also introduced in our toolkit a proper tracking algorithm in order to mitigate this effect. Parallel support has also been added, as well as an efficient iterative-based characteristic mode analysis solver to allow users to also solve or calculate characteristic modes for larger and more complex structures, such as the vehicle type of example that I showed. Yes, and I've also illustrated CMA, its useful properties in various applications, such as that in the mobile phone example, but also in the MIMO antenna design. I would like to thank you all very much for listening to this webinar on characteristic mode analysis, and I also would like to emphasize that if you have any specific queries or even recommendations, please do not hesitate to contact us at webinars@feco.info. Now, before addressing some of the questions that was asked, I would like to demonstrate to you in our FECO toolkit what CMA actually looks like. Now, this is called CAD-FECO, which is our GUI or graphical user interface. And I've already set up a very simple structure here, which is a PEC plate. This rectangular PEC plate, as I've shown in the presentation, has a specific modal distribution. And our goal is now to calculate this modal distribution using FECO. Now, firstly, to set up a CMA request is very easy. We allow that integrated as a tab here that says characteristic modes, which the user can click on, and then you can specify the number of modes that you wish to calculate. We provide a default number here of 6, but you can change this quantity depending on how many modes you wish to consider, which is again directly related to the amount of computational effort you're willing to spend. Now, as I said, as of FECO Suite 6.3, you can also choose to include the effect of a modal of excitations by ticking this box here called Compute Modal Excitation Coefficients if the sources are present. And what it would then do is calculate the effect of the excitation on each of the modes, from which we can then deduce quantities such as the modal weighting coefficient or also the modal excitation coefficients. I will show this to you later when considering the post-processing tool. I can then go about simulating this in our kernel, which I'm not going to do now, but the results can then be pulled back into our post-processing tool called post-FECO. Now, in the previously example, I did not only include a characteristic mode request, I also included a standard simulation, which is just a full wave MOM analysis of an incident plane wave on this type of structure. That is, no CMA, just I would like to get a reference solution. So both of these solutions are then displayed here in our post-processing tool, the first of which is our reference solution. And this result here is a very typical, well-known current distribution for a rectangular plate of these dimensions, in that we see the current are maximum here at the edges and tapers off near the center. Now, our characteristic modes also looks similar. If I can just hide the characteristic far field here, we offer you the eigencurrent display here on the 3D graph, but you can also iterate through the various mode indices to see the eigencurrents that are supported on this structure. And one can also do this at different frequencies. Now, as I said, viewing only the eigencurrents or the characteristic far fields, let me just quickly iterate here through the far fields, you can do exactly the same with the characteristic far fields over here. That is, iterate as a function of the mode index. Now, if we calculate, our modal solver also calculates the eigenvalues, which you can display on a two-dimensional graph as a function of, for example, frequency. Illustrated here are the first 4 modes associated with the PEC plate. Now, as I said in the previous in the presentation, it's not always easy to obtain what is happening here, even by zooming in. And to this end, we've also included other quantities, such as the modal significance as a function of frequency, which allows us to more easily obtain the resonating properties of certain modes. Likewise, you can also extract, for example, a characteristic angle as a function of frequency. And if we now account also for the source, and the source in this case will be the incident plane wave, we can also look at, for example, the modal weighting coefficients. And just to summarize, the modal weighting coefficients are these complex scaling coefficients that include the modal excitation coefficient, which is the numerator in this formula over here, essentially the effect of the excitation in each of the modes, divided by the 1 plus j times the eigenvalue. Now, these quantities can be plotted as a function of mode index, so we can see that most of the power, or the mode that will be excited most efficiently by applying an excitation, such as the one illustrated here, is this mode number 1. And if we go back to our characteristic mode solutions, and we look at mode number 1, we see, that was the far field. If we look at mode number 1, we see that this current distribution closely resembles that of the full weight reference solution. Now, I'd just like to address a few of the questions that have been that were asked in the during the presentation. The first of which is, could you let me know where the presented material is made available? The presented material will be emailed to you as soon as the webinar has been completed. You will then get a link in the email where you can download this the whole webinar. The other question is, in slide 13, you showed a structure, a dipole, and its first 3 modes, where the first mode has a large power and the other modes almost no power. You also show an excitation on the structure. Is the excitation necessary? Well, the excitation is not necessary. It just provides useful extra information, such as I showed here, the modal weighting coefficients, and you can also deactivate the effect of including the excitation in the calculation by unticking that box over there. And I just want to emphasize again that characteristic mode analysis is essentially a source-free solution. But it is also important to note that not all of the modes will be excited easily by the applied excitation, and for that reason it is important to also look at quantities such as the modal weighting coefficients where possible. The other question is, how is it included in the calculation of modal power? This also is related to the aforementioned question, in that is excitations necessary? Now, modal input power is derived from the modal weighting coefficient, or this quantity alpha over here. If I can go back to our slideshow and bring up this slide over here, modal input power is defined as half of the sum of the square of the magnitude of these modal weighting coefficients, which is essentially the weights associated with each of our individual current modes. The other question is, does the position of the excitation affect the characteristic modes that are calculated? No, the characteristic modes are calculated in absence of the excitation. We only calculate these modal weighting coefficients then as a further step when we look at the excitation. But from that, we also calculate the relative mode power. Now, to just expand on this question, is the relative mode input power will of course vary if you start moving this feed around or add more than one feed in order to excite, for example, higher order mode behavior. The other question that we had is CMA going to be implemented for dielectric bodies? Characteristic mode analysis has already been implemented for dielectric bodies, and I would like to emphasize, I showed this at the end of this example of the complex type of a feed structure over here, which was modeled using surface equivalence principle. The other question that we had is, how can we combine 2 or more modes to get a hybrid pattern, and how to apply excitation to get this combination? And this can easily be done in our post-processing toolkit, in that we offer a scripting environment called Lua. And in this scripting environment, you can use quantities such as the characteristic fields, which you can then also scale with other quantities such as the modal weighting coefficients, or even your own type of defined weighting coefficients that you wish to define or calculate. You can then deduce, for example, your own weighted set of characteristic fields, or as a function of a summation of a few modes, and this result can then be viewed on, example, a 3D graph. Thank you all very much for attending this webinar. I hope that the information that was provided is sufficient, but I also would like to just emphasize again, if you have any questions or even any recommendations, please do not hesitate to contact us at webinars@feco.info. Thank you for your time.